This is joint work with Jordan Snyder, a graduate student at UC Davis, Anatoly Zlotnik, who's in the theoretical division at LANL. I'm in the information sciences division, and Louis Tao, sorry, I converted this from a Mac to a Windows. So anyway, Louis Tao is at Peking University, and he and I have been working for 6 or 7 years now on understanding mechanisms that we can use for implementing computations in neural systems. So I think really we don't need a whole lot of motivation here. People have been talking about backpropagation, and that might be a killer app for neural systems. It's clearly the workhorse for much of current machine learning. Deep nets are based on backprop. And the interesting thing about backprop is that it's inspired by neural systems. You know, the feed forward essentially is inspired by V1, but it's inherently difficult to implement due to the non-local learning. And in fact, it's not actually non-local learning that's the issue. It's the need to get information from one part of the circuit to the other in order to do the learning. But people just typically call that non-local learning. But the real reason is because last year at the ICONS meeting, Mike Davies, in similar comments to what he said here, effectively said it couldn't be done, and I like a challenge. So first thing I should say is that a couple of things will have spikes in them, but the formalism that we put together is a mean field formalism. So I'm not going to be getting to what Johannes was, wanting a spiking backprop. That's kind of the next thing that we're working on, and we'll see if that works. But I'm going to start off talking about SynFire chains, and then about gated SynFire chains. So we've come up with a mechanism for gating information through a neural circuit in a faithful way, in particular for gating graded information through a neural circuit. I'll tell you how to compute with these gated SynFire chains. I'll tell you how they can interact with learning to turn on and off learning processes. And then I'll talk in detail. In fact, you may be concerned with at least one of the slides that I present in Backprop. We're going to get down into the weeds a little bit. So a SynFire chain is a bunch of feed-forward layers. They have to be, so here, this is the initial layer. This is a final layer. You put a volley of spikes into this layer, and it propagates as long as there are enough spikes that you put in, and as long as the coupling is big enough, it propagates through these layers. And so this was put forward in 1982, and I think for quite some time, people just felt like, hey, we know how to propagate information through neural systems. The problem, and the hope was that, or I think people in their heads, because they didn't get into the details enough, quickly enough, we're thinking that this information that you propagated could be graded information. So by graded, I mean that you have a firing rate amplitude. It can go faithfully from one layer to another. But what was shown in this famous paper in Nature is that if you look at these volleys of spikes and you look at the standard deviation and the amplitude, very rapidly the amplitude goes to a fixed amplitude and the standard deviation goes to a fixed standard deviation. And so that's a problem. It means that you can propagate one bit of information from one layer to another, but you can't propagate graded information in this way. So that's unfortunate if you want to do things, even to some approximation, use things like real numbers in your circuit. So Louis and I were thinking about this problem because of a particular project that we were working on. What the idea that we came up with in order to fix that issue was to do this. We could take a population of neurons, we separate out a control population and an information population, or a set of control populations, set of information populations. And if the control population can generate a pulse that will push the information populations up to threshold, then incoming information into these populations will be able to propagate downstream. And you need a sequence of pulses that sequentially gate the information downstream, which is costs you some neurons, but it's a way of faithfully propagating the information. And so if you implement this we came up with a way of implementing this in an integrate and fire network. And what we did was we used the actual original SynFire chain, which locks to this attractor very quickly. We used that to generate the gating pulses. So it's very well controlled, very, very clock-like in a lot of ways. And it made these beautiful gating pulses. And then we can take those pulses and couple them to what we call a graded SynFire chain, and we could get this nice graded information propagation. So here on the top, we're just getting one pulse that's going from one layer to the next, and we just show a few different amplitudes where we can do that. So and we did, this is, I'm not going to talk about it much, but we have 2 or 3 papers on how to get that integrate and fire network via a Fokker-Planck approximation down to a mean field approximation. But this is a mean field approximation. So each of these traces, these are in cyan is the currents. This is one population upstream. This is a downstream population. And this represents a population of neurons, not just an individual neuron. So now we've gone from spiking to mean field. So here, if there's an upwind current that's at some value, if we inject a gating pulse, it'll push that current above threshold, and all of a sudden you've transduced the current into a firing rate. That firing rate goes downstream and gets integrated in a current. And then if you have a subsequent pulse, you can do that, and you can faithfully propagate the information downstream in a faithful manner. In an actual integrate and fire network, it's not going to work forever. In the mean field one, it will. And we're working on ways to make, to worry about how far we can propagate this information in one of these networks. But now, for now, I'm just going to actually use, in the subsequent stuff, I'm going to use a discrete mean field model, which is just to say that I know, if I know this current at some time and I'm using a gating pulse, then I can know that the current's faithfully propagated to another time. Okay, so as it stands, I've shown you that I can take a graded amplitude and firing rate amplitude and propagate it between a bunch of layers. So that would be nice for instance, for a short-term memory, where I can just make a little loop and keep some information in the loop. But I'd like to be able to process information as well. So let's think about a vector of these populations. This is the mean field model that would be associated with it, and in particular, there's a matrix in here which is synaptic connectivity. And so, and this is a gating pulse, and what you can do is to gate a linear map between vectors of neuronal populations. So, in fact, these are thresholded linear maps, so these are basically gated ReLUs. Okay. So far we can propagate information, maybe use it as a short-term memory. We can process information going from one layer to another. In terms of how can we use one of these SynFire-gated SynFire chains, how can we use it to interact with learning? So another project that we worked on was to understand that. We took an autoregressive process as input, and we ran it into a set of short-term memories. So for an AR process, the important thing is the lagged covariance. If you want to make a prediction, you need to have an estimate of the lagged covariance. But if you run, if you keep these lagged, this process in lagged memories, in these short-term memories, what you can do is, so we're assuming a first-order model for Hebbian learning, and it requires that pre- and post-synaptic firing rates have to be positive at the same time for a modification to happen to the synapses. And so what we did was we used gating to, we'd gate the different lagged values of the autoregressive process to pre- and post sides of Hebbian synapses, and then that turns on the learning, and we could learn the lagged covariance that way. So for instance, here are some covariance matrix which you can see converging to the appropriate values. So one of the other things I want to say here, because it's in this plot, you can see that I have one autoregressive input, but I have pairs of short-term memories. So if you have a computation that has real numbers in it, you can't keep negative numbers. Somehow you have to have positive numbers. And so we started using what we call push-me, pull-you pairs in reverence for Dr. Doolittle. So for a push-me, pull-you pair, what you can do is arrange that the information that's coming in, if it's positive, goes into one population in the pair. If it's negative, it's a positive firing rate, but in the other population in the pair. And so this kind of doubles the size of your synaptic connectivities, but it works. Okay, so we're getting down to backprop, and I told you we'd get into the weeds, and here we are. So using these different mechanisms, in a standard backprop protocol, we have input coming in. We have to be able to compute network activity. We have to be able to compute a ReLU of network activity. We have to compute the derivative of a ReLU, as a function of the network activity. We have to be able to compute errors and propagate the errors backwards through the transposes of the matrices, and then we have to be able to use the errors in these layer outputs in order to update the weights. So what I want to direct you, so the difficult things here are computing these derivatives and computing these Hadamard products, which are just element by element products of a couple of vectors. And so what we do here in order to do this, so for instance, I need two derivatives and I need a Hadamard product. So what we do is we use this property of the SynFire chain. So far we've got a SynFire, a gating chain, which is a standard SynFire chain, coupled to a graded chain, which is the chain that contains the information. And so far it's always been the gating chain couples to the graded chain. But if I allow the graded chain to couple to the gating chain, then if the graded information comes in above this threshold, then I will turn on a new gating chain. If the gating chain comes in below the threshold, it will not be turned on. And so so I'm going to assume that our activity function for the neural net is a ReLU, and the derivative is then the pulse that's generated in the synaptic chain we can use as the derivative, the Heaviside function that's related to the ReLU. And furthermore, in order to implement this Hadamard product, we can take, so we take a vector of network activity, we couple it to a gating chain, or actually a vector of gating chains. That gives us effectively a mask And then that mask we can use to gate downstream information which is related to the backpropagating errors. Okay? So sorry, but it's that much of a pain in the butt to do this. So the mechanisms that we've got a gated SynFire chains. We can construct short-term memories. With these push-me, pull-you pairs, we can encode real numbers. We can gate this ReLU thresholded activity. We can also gate the derivative, the theta function or Heaviside function activity using a gating chains. And by using these as gating chains, we can implement Hadamard products. And then by simultaneously gating the graded information related to errors and to outputs, if we gate that simultaneously to two sides of a synapse, we can update the synapse. So that's everything that's involved. And this is the slide that you're going to love. OK, so this is one layer of backprop in this pulse-gated framework. So here, and let me just kind of go through it. You should, so I didn't get it yet on the archive, but on the bioRxiv, but it will be soon. And you really need the full caption and the text in order to get this, but let me just walk you through a little bit. The feed-forward part of the network is in here. The X's are the input, the N's are the network activity, and the O, these are some holding stations, and the O is the output. T would be, for just a one-layer network, this would be an expected output that will be compared with the O. And then that comparison gets gated by these guys here. So let me keep going. So the error backprop parts are these populations here, including all of the Ds and these populations. And all of this is controlled. The information flow through the network is controlled by the gating populations here. And then the short-term memories. So for instance, we're going to need, so there are two synapses here, which I'm going to need to update, two sets of synapses. Those synapses, I'm going to need to write in an input and then take error information, gate it back to, so this is pre and post-synaptic, and I gate this information both at the same time using this gating population here, and I update my weights. And so this whole circuit is going to be iteratively, run through iteratively many times until the weights converge. So here is the derivative of the ReLU is computed here, P, and then it's saved in some memories, and then it's used to gate the errors into these populations. And like I just said, simultaneously gating in order to update the weights. Okay, so for just a single, layer, this was just using one push-me, pull-you pair. We wanted to learn just the identity operation. And so you can see rapidly the weights go to the correct value. This is just a blow-up of the initial convergence of the weights. And down here are some errors. The errors depend on the time constant that you set for Hebbian learning. If you set a longer time, so the time constant's the effective window over which you're averaging information. And so this one had a longer time constant than this one. But they go down to small values. I'm not going to talk about this. That's what you need to do for intermediate backprop layers. But in general, okay, I guess here, so on the right-hand side, we kind of think in terms of these schematics. We have a memory that we have to be able to write the input into. We have derivative that we have to use in combination with the previous errors in order to compute an error. Then we have to write this error to the postsynaptic side and write this to the presynaptic side. And we end up with the appropriate update. So here we constructed a two-layer network, for which this is another schematic like that. So we have X, we can write it into some memories. We generate the network activity and the derivative. We have a memory to keep that in. We compute the output for the first layer, keep that in memory. The second layer, network activity, second layer, derivative, second layer output, compare the output to the expected output, compute an error that makes use of the derivative here, keep that in memory, and so forth. We do the update. We have to do 2 updates of W1 and W2. We also have to update the W2 transpose in order to correctly propagate the errors back. But we can do that, again, just by making sure that our gating pulses are doing the right thing at the right time. So here for the 2-layer circuit, the first layer, this is just XOR logical function. You can see the push-me-pull-you pairs are a little bit wasteful of populations. And so you can see lots of these weights are actually just converging to 0, but a couple of them are necessary, high and low. Here in the second layer, we have 2 that both go high. The rest converge to 0. And the error goes down to some local error. But for an XOR, you can round and actually get 0 error. That's the purple trace here. OK. So the point here is that you can use pulse gating as essentially a control network to get information where you want it, when you want it, in one of these, in a neural circuit. You can use it to construct these effective activity functions that are necessary for backprop. You can use it to turn on and off learning when you want it. And using these mechanisms we've implemented in a mean field setting, the backpropagation algorithm. This circuit overcomes the problems of non-local learning by using this SynFire-gated SynFire chain kind of an operating system, right? So this is these gating populations are acting alongside of the information-containing populations, and they're controlling what that information is doing as it goes through the circuit. So that's it. Thank you.
Thank you very much. Time for a question or two. Julia.
Thanks. So I was the one who preached for necessity to have some structure, right?
Yes.
But this is a lot of structure here. Is there some evidence that something like that is maybe present in the brain, or is it like the minimal necessary circuitry to do this kind of stuff?
On the neuroscience side of things, I don't think so. On the other hand, when you run these kinds of circuits that are iterative, right? What do you generate? You generate oscillations. So last year, I talked about a circuit for doing synaptic copy. And one of the things that we found since then that we didn't present last year, but was that in order to copy recurrent connectivities, one set of synapses to another, there had to be a quadratic relationship between the 2 of the frequencies. There are 3 oscillation frequency, and there had to be a quadratic relationship. And if you look at the data that comes from non-REM sleep, when people are maybe copying memories from their hippocampus to their frontal cortex, they're related in the same way that we had to have to put together the circuit. So we got into this kind of research because I don't like the way standard neuroscience is done. I don't like putting together some complicated circuit with whatever that we know from anatomy and biophysiology and turning it on and seeing what happens. So I feel that this is a way, from the point of view of theoretical neuroscience, this is a way of putting together a structure that does something that may or may not be useful, but then you can ask the question, is there something in some other neural circuit that we can measure in the brain that's doing something similar? And presumably there could be crosstalk between them as well. So yeah.
Okay. One more? Okay.
Thanks.
No, there is another question for you here.
Sorry.
Don't run away yet.
I was just curious if you, because it looks like the activity is pretty sparse, and if you knew roughly what level of activity you're seeing.
So we don't have spikes. So it's definitely sparse because there's only ever information in so what we put together is not optimal. And I don't think that nature probably would have come up with this. To a certain extent, you could think of this as well, you could use this maybe industrially in a neuromorphic chip. But probably if you needed to put this structure together, you would optimize things. You would make use of multiple units at the same time. You could probably do some learning at the same time you're propagating some information. And there's kinds of optimization that you can do. Here, I showed lots of different weights that needed to be updated. You can reuse weights, and so then you can use more memory populations. So it's a moving target, and certainly if we're going to try and put this on Luihi, and I'm sure we're going to find out a lot when we try and do that.
Something like liquid state machine.
I don't know.
Okay.
Yeah, let me not conjecture.
I think we need to move on there, so let's thank Andrew again for his talk. And